at the start, t equals 0. Let's just say that my object has a translational velocity, but is currently not rolling. It's not spinning in any way. It's just sliding. And we'll say that this part of the surface has no friction. But when it makes it to here, there's friction. All right? The moment it hits the part of the surface where there's friction, there immediately springs to life a frictional force that acts at the single point of contact between the ball and the ground, right? Suddenly there's friction. That friction acts on the center of mass. Therefore, during this time, the net force equals ma. And this acceleration is slowing the velocity. So v is decreasing. Everybody understand that? Because I have an unbalanced force to the left. At the same time, there's an unbalanced torque. But this unbalanced torque is causing a positive change in the rotational velocity. So during this time, the rotation is increasing. So omega getting bigger. However, during this moment, v does not equal omega times r. Can't count on that. They're not related yet. This is rolling with slipping. Well, this is just plain old sliding. Now, this number is going down. This number is going up. R isn't changing. There's going to come a moment when V equals omega R. That moment, the moment that that happens, then we have rolling, or rolling without slipping. At that moment, this point of contact is instantaneously at rest with the surface. I'm going to say that again, and I'm going to even zoom in. This point is instantaneously at rest with the surface. It's hard to understand this, but this is actually the pivot point for the rotation of your object about the ground. The problem is that when it rotates about this point, a moment later, this point comes into contact with the ground. So the point that's in contact with the ground is always changing. But that point that's in contact is the pivot point, and it's instantaneously at rest with the ground. Moreover, we've reached a point where the velocity and the angular velocity are now in sync. Because of that, once we reach a state of rolling on a level surface, the net force can be 0 and the net torque can be 0. Nothing is required to maintain motion. That's Newton's first law. So once this occurs, those two things are true. There's other things that are maybe interestingly true too, like the fact that the very top of this wheel is going 2v. Because the top is moving fast, the bottom's not moving at all, right? It's instantaneously at rest. Some people find that part hard to understand, and that might take a day or so. But as I approach the end of the class period, let me tell you the few other things I want you to know. First, this is the kind of space that AP likes to play in, to really see if you understand, to ask nuanced questions about how something transitions from sliding to rolling. But they also like to take that same problem and perhaps put it on an incline. Here, the forces would be unbalanced. The object would not be able to go up the ramp and maintain rolling unless there was suddenly some friction. That friction is going to act to slow the wheel down, and its direction becomes complicated. So as we look at the relationship between translational motion and rotational motion, it's not as straightforward as I'd like it to be. It can be a nuanced conversation. We're going to take a deliberately simple approach to it in the beginning, and then add some layers to it as we go. And the first one I've given to you is right from your homework, a place that I want us to start. This will be the first one we do when it comes to a rolling problem and activity. In this problem, it's a ribbon wrapped around a disc, or it's a string wrapped around a ring or a ball or something like that, or a yo-yo. They're all the same kind of problem in that gravity is going to cause the object to unroll a string or unroll a ribbon. So when I was asked earlier why I had toilet paper on the floor, it's simple. It's this problem. The unrolling of the ribbon as it falls to the ground, there's enough inertia in the roll itself to prevent the roll from falling at G. It falls at something less than G. In fact, I'm asking you to tell me what the acceleration would be if this unrolls without slipping. To do so, you have an unbalanced torque problem that you have to solve. And this problem starts with you figuring out where's the pivot point. And I don't think it's obvious. Do you place the pivot point here, or do you place the pivot point here? So raise your hand if you think it's 1. Raise your hand if you think it's 2. Or just give me a 1 or a 2, that's a good idea. All right. You might be surprised that due to relativity, and I don't mean Einstein's relativity, I mean relative reference frames. It doesn't matter whether we ride along with the toilet paper or ride along with the unwrapping ribbon. We can choose this as our pivot point or this as our pivot point and get the same answer. We're going to do 2 as our pivot point first, because we can finish that in the 3 minutes that are here. We'll do 1 as the pivot point tomorrow. If we use 2 as our pivot point, then our torque is going to come from the force of gravity. There are 2 forces acting in the system. There's the force of gravity acting downwards, and there's tension acting upwards. The tension has to be less than mg, or the system can't accelerate downwards. So net force will be mg minus tension equals ma. Net torque, on the other hand, is going to equal I alpha. But since this system rolls, we are guaranteed to be able to use this relationship to replace alpha with A. Now, normally I would want you guys to do more here, but I'm going to have to do this. If this is our pivot point, we need to use the parallel axis theorem to determine the moment of inertia. It's a disk, so 1/2 mr squared. We are shifting point of rotation, one radius. So our moment of inertia will be 3/2 mr squared. Our torque is pretty easy. The torque arm length is r, the radius. The unbalanced force is mg. And our inertia is 3/2 mr squared times a over r. I brought all the pieces together. Now, you see that all the r's are going to cancel, right? Do you see that the m's are going to cancel too? That gives me g equals 3/2 a, or a equals 2/3 g. Now, your job is to do the other one. Do it about the center. We'll do it the first 2 minutes of class.